Next up is a very cool Python package called Scikit-Learn that a lot of you were asking about. So this is a machine learning package, and this allows us to do things like random forests and clustering, for example. So random forest is a meta estimator that fits various decision tree classifiers on subsamples of your data, and then uses it then generates a fit and or a classifier that you can then use to classify additional data. So typically what you'll do is if you have, say, 100 data points, you'll take 80 of those data points and build a classifier, and then you can classify the remaining 20 and see how well it works. This will give you a sense of how useful the kind of data that you have would be for classifying new data. You could also take all of your data and build a classifier, and then go out and collect new data and classify that. But you'd want to be cognizant of batch effects and things like that. So what we're going to do is use this famous machine learning data set, this iris data set, and use that as an example. So we're going to import that from Scikit-Learn data sets. We're going to also import the random forest classifier function, and we're going to set a random seed. So if we want to learn a little bit more about this random forest classifier, we can just type the name of that command. And notice in this case there is no sklearn.random forest classifier, because we imported that function directly. So if we had instead imported just sklearn, then we'd have to type sklearn.ensemble.random forest classifier. But since we imported it this way, we can just type that function by itself. So if we execute that cell, it's going to give us all this information about how this function works. And we are going to use a couple of parameters. One that we'll see in a minute is the number of jobs, which is just how many jobs are running in parallel, and then the main input data. Okay, so I can turn that back. So what we're going to do is save that. We're going to use this load iris method to create data from that data set. We're then going to create a pandas data frame from the data and the column names, which are stored in that data object, and then we're going to just have a look at the data here. So we have 4 features that we're going to use to do a classifier. We're going to do sepal length, sepal width, petal length, and petal width. But to do the classifier, we actually need to import also the information about what we're classifying, which is what species the data come from. So there's 3 species in this data set. So we're going to add that column to the data frame using df bracket species, and then we're going to just use this pandas kind of helper function categorical from codes, which is going to just get the data from this data set. So this is going to end up giving us the species column in addition to all this feature data. So next what we want to do is create a training set, and then a set that we're gonna that's going to be test data. So what we're going to do here is just for each row in the data frame, we're going to generate a random number from 0 to 1. And if that random number happens to be less than or equal to 0.75, we're going to call that our training data. And if it's not, it's going to be our test data. This is just going to divide the data up, where 3/4 of it's going to be training data, and the other quarter is going to be test data. So if we now look at that data frame, we have this column is train, and by chance we don't see any is train equals false, but I promise you they're there. In fact, what we can do is do df is train dot value counts, and this confirms that we have 118 rows where that is true, and 32 rows where this is train is false. So now what we can do is, if you remember when we did the masking or fancy indexing, we can say if this column is true, save that to a new data frame called train, and if it's false, save it to a new data frame called test. So we're going to create two new data frames, and then we're going to just print, how many samples are in each data frame using the length function. And so this is going to match, what we had here. So we have 118 in the training data and 32 samples in the test data. Okay, so now we're getting close to actually being able to do the random forest classifying. So now what we want to do is get the feature data. So we're just going to get the first 4 columns of that data frame which have the feature data. We're going to call that features. And in fact, we're not actually getting the columns themselves, we're getting the column names. So we're just getting the four column headers for those 4 columns. Next, we want to convert those species names just to digits. So we're going to use this another pandas utility function that we haven't seen called Factorize, and this will convert those names to just 0s, 1s, or 2s because there's 3 different options. So now we'll get an array of 0s, 1s, and 2s corresponding to those 3 different species names. And now we can actually make our classifier. So the first thing we do is we initialize the classifier, and by convention we're just going to call it CLF, and that's going to be created using this random forest classifier function where we're going to set number of jobs as 2 and random state is set to 0. So just an initialization state, and for parallel computing we can specify how many jobs we want to create in parallel. Finally, we can actually do the we can actually build the classifier or train the classifier. So we're going to take our training data set, this is a data frame, and we're going to get those 4 columns. So this features corresponds to those 4 columns. And so that's going to be our feature data that we're going to use to train, and then the output is the species numbers 0, 1, or 2, and that's going to be specified by this Y array. So when we don't worry too much about the future warning, it's going to just generate this output where it tells us all of the parameters that we used. But now we have created this we have trained this random forest classifier, which is stored in this CLF object. So if we want to now apply the classifier to the data, we can now use this predict function. So we're going to do clf.predict, and then we're going to pass it the test data, just those features columns, because again it's a classifier that was trained on those 4 columns, so we're going to use those 4 columns to then predict the species for the remaining data. So once we run that, it's going to give us a number. This is going to be the species of each of those training rows. So we'll have to go back and look at what those are. But what we can also see is the probability of each of those test rows being each of those 3 species. So here it's quite, for these first 10 at least, it's quite confident that it's 100% sure that based on the classifier that we've predicted the right species. You can dig deeper and look at the whole array if you want to. In fact, let's just, so there are some here In fact, let's just yeah. So we can see there are some where it's not sure, could be one or the other, but for most of these, it's the probabilities are pretty good. So how we would then evaluate the classifier is, one, we can look at the actual English names and what they actually were. So in fact, it would be good to let's do this. Let's create a new data frame called results. And then we can do results predicted equals results actual equals this. Hopefully this works. These do not match up, unfortunately, so oh, I bet I need to reset. I need to reset the index. I'll come back to that. I'll come back to that. So what happened was when I did the test set, let's do yeah. Okay. So let's see if this works. There we go. Okay. So we can see that the results are very good. In fact, let's see if I can find any examples where it's misclassified. If I go back up and I change the number of, let's do this, change the number of rows displayed. We can see there, okay, there's a couple here. There's these two, rows 16 and 17 are misclassified. So this is another way we can review the results. So if we look at all of the data, I'm going to move this up. If we look at all the data, we can do this using a confusion matrix. So we can use this pandas function crosstab, which I won't go through, but this will tell us the how these two data sets compare across the different the samples, and we can see there were indeed two that were misclassified, where they were actually versicolor, but they were classified as virginica. We can also get a measure of which features were most important in classifying. So petal width and then petal length were more important for classifying than sepal length and sepal width. So this is also really valuable information. So there's one more thing I wanted to cover with Scikit-Learn, which is k-means clustering. So what we're going to do here is create a two-dimensional array. So we're going to plot x against y, and here's what the data look like. And we want to cluster these into two groups. So by I, we would expect that we're going to get a cluster down in the lower left and a cluster in the upper right. And this is going to be using k-means clustering. All we have to do is specify, first we create a k-means object, which takes this k-means, which is the output of this k-means function and the number of clusters that we want. So we're going to say n clusters equals 2. And then that object we can then fit onto some data, which is this two-dimensional array that we just specified. So this will now give us, if we use this attribute cluster centers, it will give us the coordinates of those two cluster centers. We can also get the labels that correspond to each of the points in the array. It will say whether it's cluster 1 or cluster 0. And so the way that we can then plot these data is to first we're going to plot the same data, but we're going to pass this C, which stands for color. So we're going to color by the labels, and then we can just pass a color map, which will just pick. It will just allow us to pick two colors from that color map. And so we have the one cluster in red and the other cluster in blue. If we wanted to do 3 clusters, all we'd have to do is, when we create that k-means object, we just say n clusters equals 3. We then fit to the data and then plot it again. So it's a little hard to see on my screen, but it's you can see there's the greens up here, the reds in the middle, and the blues down here. So that is a very quick tutorial of Scikit-Learn. If you want to learn more, there's a lot more information at scikit-learn.org. And oops, you can do, so we did classification and clustering, but there's also regression options. There's dimensionality reduction, which is super useful, model selection, pre-processing, and it's a very actively developed package. Would anyone like to see the microbiome stuff, the Scikit-Bio? I can go through it quickly. Okay. This could be useful for other things besides microbiome. It's useful for any kind of amplicon data, but I think a lot of these concepts would be useful for other kinds of data. So basically, Scikit-Bio is a specialized Python package for biology, much like Scikit-Learn is a special Python package for machine learning. Like I said, I had an issue with the installation on this with some versions, and I don't want to. Let me see if it'll run on this machine. Okay, so it's not. Let's just try it out. We've already done everything else, so I'm gonna. So here's my terminal. I'm gonna conda install. What this is a conda install, and then this -c is channel. So this says I'm gonna get Scikit-Bio from this channel of Anaconda because it might not recognize this as a regular package. It might be only a package you can see if you know where to look. So hopefully this will work. And what this is going to allow us to do is work with what we call OTU tables. These are observation tables. OTU is a acronym that means operational taxonomic unit. This is like a species. So for microbes, we don't really have a species concept, so we use this thing called an OTU in place of the species. So, well, let's go ahead and I can show you the version on GitHub, and we can just look at it. Unless this is ready to, no. So the static version on GitHub is fine for this, so I'll scroll down to the bottom. Okay, so we imported all this stuff from Scikit-Bio. So what we can do is we just created an example table with some data that have rows and columns. And so one option that we have is to compute alpha diversity. So alpha diversity is, there's different metrics that we can use, but like it's a measure of how much diversity is in each sample. So for example, we can use observed OTUs, and then we pass the data and the IDs, which are basically the column headers, and it will compute the number of observed species in each sample. We can actually read in a tree different ways. One way is we can read it directly as a string. We can then compute a phylogenetic-based alpha diversity, which is called, this one's called Faith's PD, or Faith's phylogenetic diversity, which uses the tree to determine how much phylogenetic diversity is in each sample. We can also use the tree to compute beta diversity, which is the distance between the samples from each other. And phylogenetic distance is a really useful idea with the distance between samples, because if two samples are different but they contain very similar species, then they should be more similar than a third sample that has very different kinds of species in it based on the phylogenetic tree. So this is a so actually this first one here is Bray-Curtis distance. This is not using phylogenetic distance, but it's just using a more traditional distance. But unifrac is a phylogenetic beta diversity metric, so the Scikit-Bio allows us to compute that as well. We can also determine if the distance matrices are correlated, so we can compute a Mantel test to see if the weighted unifrac and the Bray-Curtis distance matrices are correlated, and it appears that they are, that the p-value is less than the alpha that we set up. And then we can also perform a dimensionality reduction. So we saw that we could do this with Scikit-Learn. We can also do this with Scikit-Bio. We can compute a principal coordinates analysis on the unifrac distance, and we can then add some metadata to these samples, so body site and subject ID, and then we can plot the results. Here we're plotting the three-dimensional principal coordinates analysis by subject. This is by the person, either it's person 1 or person 2, and we don't really see a clustering by subject. But if we then plot and color by body site, we can see that there is some clustering. We have these tongue microbiome samples here, and skin microbiome samples here, and gut microbiome samples here. So there is some clustering. We can then look at the strength of the clustering. And so one way we can do this is using ANOSIM. And if we try to look at clustering by subject, we don't get a significant result. It's the p-value is not less than 0.1 in this case. But if we look at clustering by body site, we do get a significant test based on this test statistic, or based on this this alpha. The p-value is less than the alpha that we we set. I think this is the last thing. Yeah, so now we can also look at correlations with metadata. So we can look at, we can add to our data frame the alpha diversity data that we computed, the number of OTUs or the phylogenetic diversity, and we can then look at box plots by body site. This is only 2 subjects, so we don't have a lot of data here, but we can look at box plots, and we can also look at, say, whether the these 2 distance matrices, or rather these 2 alpha diversity vectors, are correlated. They should be. So we can do a Spearman correlation and see that we have pretty good correlation between these 2 different alpha diversity metrics. Of course, each one is perfectly correlated with itself. So that's a really quick crash course in Scikit-Bio. If you do microbiome research, you may have heard of QIIME. QIIME uses a lot of these functions in it. You can do all this stuff in QIIME directly, but you can also do it in a Jupyter notebook using Scikit-Bio. QIIME itself also has a notebook type interface. Finally, we covered this earlier in the course, but if you want to use R in Jupyter Notebooks, the instructions are here. So if, for example, there are some statistics that you want to do that aren't available in Python, or if you just prefer to use an R function that you're familiar with, you can still use this handy notebook environment to do R. So that's all the statistics stuff I wanted to talk about for the course. If you have specific things that you're trying to do that we didn't cover, let me know and we can try to figure it out. So that's it for today, and then on next time we will do interactive visualization.